Hi, my name is Ross Anderson. I work for Google Research. I work on the operations research team, and today I'm going to show how to use OR tools, specifically the MathOpt library within OR tools from Python to solve the facility location problem. See here, I have my IDE PyCharm open. So first thing, we need to install OR tools in my virtual environment. Find it, install. And I'm going to do a visualization, so we will also install matplotlib. All right. So they're installing, and we can start coding while we are waiting. So facility location dot. Okay, so make this nice and big. Okay, so let's just write down a statement of the problem first. So we're going to solve the capacitated facility location problem. And I'll define that below. So our input, the data. We have facilities. And we're index them over I. And there'll be m of them. There are customers. And we have a limit. Oh, we have a distance, sorry. Of how far it is from facility I to customer J. And last, we have a limit L on how many facilities we're allowed to open. So L has to be less than M for this to be an interesting problem. Okay, so, and our goal is to pick L facilities open out of M to minimize the average distance from a customer to any facility. Okay. So each customer will go to the closest facility which you have opened, among the ones you've opened, and we want to pick a subset of the facilities to open to minimize this cost. And now we'll write down an optimization model. And the model is a little bit subtle, and we'll maybe talk a little bit more about it later about different variations of the model, but this is just kind of a textbook model for the problem. So sum over I, sum over J, distance ij. Oh, sorry, I forgot. Jump the gun here. What are our decision variables? So write those down before we write down our model. So xi is a binary variable. Do we open facility I? And yij. So we're going to model this as a continuous variable in 0, 1. It's actually implied integer, so if you made an integer, that would also work. Solver's a little bit better if it's continuous. Do we serve customer J from facility I? Okay, now we have our variables, so we can kind of go back and write down our model. So sum over I, sum over J, dij, yij. So this is saying minimize the total cost to serve all of our customers. What are our constraints? We have look at all the facilities that we picked. Use at most L of them. Okay, constraint 1, constraint 2. For each customer, we need to make sure that we serve them from at least one facility. Okay, And you could set them for more than one facility, but this will only increase your cost. So it doesn't really matter if we make this an equality constraint or an inequality constraint. And it's solver dependent, what's going to get you better behavior. But I think typically you want to make problem feasibility easy, so that's why I left the inequality version. And last, we need to say that we only use facility I to serve customer J if we actually open facility I. This is true for all I, for all J. Okay, and let's add in our xi binary and yij continuous and 0, 1. And this is a full formulation for facility location, textbook formulation. So now our goal is going to be to implement this using OR tools and MathOpt. So first things first, so we're going to solve this on a random instance in the Euclidean plane. So our facilities and our customers will just be points in the XY plane, and our distance will be Euclidean distance. So let's just generate some random input. And we'll visualize the input first just to make sure that we understand our data, and then we'll go and solve the problem. Since we don't have a bunch of unit tests, it's good just to make sure our input is good. So what is our, first we'll write down the size of the problem. M, the number of facilities, is 10 to get started, and we'll change this later. Okay. Sorry, we'll make it 20 facilities, make it a little harder. And we'll say the number of customers is 100. The limit, compliant on style, on the number of facilities we can open is 10. Limit how many facilities we can open. Okay, so now we want to write down the locations. Now the next thing we want to do is write down our D. That's the data we're missing. And to do that, we need to first get the locations of our facilities and our customers. So we'll define a function, random point, give us a random point in the XY plane. Okay. So, turn. Okay, so this will give us a random point in 0, 1 in the box starting at 0, 0 and ending at 1, 1. And we'll also, let's just do define our facilities now as random points, m random points, and our customers are also m random points. Okay, so we have m facilities and n customers. A little tricky to say. And now we need a distance function. So P1, so the distance between 2 points. So P1 and P2 are tuples here, tuples and floats, and we'll unpack them. This simple x2, y2. Okay, unpack the tuples. Now these are just floats, and do Euclidean distance x2. Turn square root dx times dx plus dy. Okay, so we have our distance function, and now we can say D is, do a nested list comprehension, distance of facilities I, visitors J, for J in and for I in. Okay, so now D is an m by n array, which has the distance from facility I to customer J at each entry. And we have all of our data. So now's a good time to draw it, to make sure that we understand it and we didn't make any mistakes. So port matplotlib. I'm a matplotlib expert, so you may see some surprising uses of matplotlib here. Did my best though to try and do a good job. Okay, and we actually didn't need the distances to draw the points, but so what we'll do, I'll make these numbers really small. M is 2, L is 1, N is 4, and we will just print our data as well, so we make sure that the plot aligns with the printed values. Actually, just put a new line there. Okay, and then we can plot our data. This is the tricky step. So we get the current axes, and we want the aspect ratio to be 1 for this plot. These details aren't too important. And we'll draw some circles. This is how you draw a circle in matplotlib. It's a little bit surprising, but it's fine. Circle just takes a point here, so we can pass the facility directly in, and a radius, and a color. Draw these guys green. Okay, and we'll do the same for our customers. We'll draw the customers a little bit smaller, and we'll draw them blue. Okay, let's run this, give it a shot. Run. Oh, we forgot to show the plot. So the program terminated. Okay. And I think that's all we need to do. Let's try one more time. Okay, we made a mistake. Customers. So, kill that and try one more time. Okay, so let's take a look at, we should have 4 customers and 2 facilities, but I'm only seeing 1 customer, so I made a mistake. Yeah, I made a mistake. One more try. So the data was good, but the visualization was bad. Okay, so our facilities are actually very close to each other, and you can see them right there. X is 0.08 and 0.07, so that's small, and Y is about 0.5. Okay, our customers, yeah, that guy 0.2, 0.08, that's here. Okay, so this looks fine. And our distances, they're reasonable numbers. Okay, so looks like our data is good. This program. All right, let's let's try and solve an optimization problem now. So I guess the next step is to build the model. So let's import our tools. MathOpt. Okay. And we'll just come out build a model right here. Actually, we'll do all the printing at the end. And okay. Make a model. And so now we need to add our decision variables. So we need x and y. So x, do we open facility I? So make all this comprehension. These are the binary variables. We can name them, can't hurt. Okay. There we go. And so decision variables. And y. This is x, I, y, I, j is do we serve customer j from facility I. So nested comprehension. As now we'll just add a continuous variable. J. Okay. Looks good. And okay, let's go back up and see what we need to do for our model. So we have our x's and our y's defined. Let's do our objective next. Sum over I, sum over j, di, j, yi, j. So we'll just make a linear expression to model the distance. And so you can check this out at 0, but it's generally better practice to use a linear expression. Keep the type total distance constant. Sometimes you get burned if it ends up being a float instead of a linear expression at the end. So for loop over the i's, loop over the j's, and we'll add in dij times yij. We can use the plus equal operator. Python lets us overload these. Dij yij. Looks good. And now we say we want to minimize the total distance that our customers have to travel. Okay, so there's your objective. Let's just objective minimize j, di, j, yij. Okay, and now constraint 1 is up next. What was constraint 1? That was that we use at most L of our facilities. That is an easy one. Model dot add linear constraint. So again, it's better to use so MathOpt is a fast sum method, and it just ensures the output is a linear expression instead of a double in the event that your list is empty that you're summing over. So you could also just call the Python sum function here, but it's better to use fast sum. And so we'll sum up the x variables because they're just a list. So this call that L. Yeah, L is our limit. All right. Next up, string 2. What was that? Okay. That for every customer, we serve them from at least one facility. So for each customer, we add a constraint. This one's not so easy, but we'll have to loop over I. We can't use the sum. Okay, so say served J. Linear expression at 0. Add up all these yij variables, and we have to serve them from at least one facility. Okay. And last constraint. This one says that we, right here, only serve a customer from a facility if the facility is open. Okay, so for each facility, for each customer, constraint that the y variable is less than the x variable. Okay, easy enough. And I think that's our whole model. So I guess we can just go ahead and solve it now. So we'll set our solve parameters to turn on the logging. Really nice. And look at these logs. Hopefully it'll be informative. And I think we can just call solve now. So pass in the model, pass in the solver type, and we'll use skip for this one. The model is basically a binary model, but CPStat doesn't do as well with all these implied integer variables, so let's just use skip. And set the parameters. Okay, I think that is enough. Now we'll make sure that we succeeded. So we have no time limit of any kind, so we know that the result will be optimal unless something bad happened. So this is in production setting. You want to do something a little bit more robust than this, but this is fine for a script. And just don't want any surprises from a bad termination reason that we have a bug in our code. And now, yeah, let's extract the facilities from the optimal solution. So what we can do, so now remember in any optimal solution to this problem, so the xi's are already binary. The y variables will also be binary. Okay, I guess like if you had a non-simplex based solver finding y solutions, you could end up with a continuous y, but at least with skip we'll always get integer y. So okay, first we'll extract a set of facilities that are open. We'll just get a bool vector. Let's take a look at that first. So okay, this is a dictionary with keys of variable values and doubles as the output. And okay, so we want values of x of I. So we can just check is at least a half. That's sufficient for what we're doing. Okay, so remember this variable values function, because we have already asserted that our termination reason is multiple, this is always defined. But if your problem was infeasible, then this function would throw an exception, so you always have to be careful here. Okay, now we have a Boolean vector for our facilities. And now let's make one more data structure, facility for customer. This is the facility serving each customer. So this is going to go over J in range N, and actually I think we have to write a loop. Okay, so it's like comprehension. Okay, so if variable values of y, I, j is at least half, then that means that we are going to serve customer j from facility I. So facilities for customer of j is I, and now we can break from this inner loop. Okay, so let's start them all at -1, and now at the end of this, I want to make sure that we did make an assignment for customer j, so we should assert that simply for customer of j is at least 0. Okay. So we just want to make sure that, so we started this off at -1 for every customer, and we want to make sure that we assign it to a value other than negative, to one of the facilities. Okay, and I think this is all the data we need. So we can print this out now. Let's get the value of the total distance. Why not? So you can extract this from the termination reason as well. We're just going to compute it by hand, because we're actually going to need it later. So easy enough to do. Okay, so now we'll print out this information. So 3 things we tracked. So, separate this, extract the solution. So leave this open. Actually, gotta remember to print out the whole distance matrix. It's a bit much. So leave a customer. And total distance. We call it objective value. That's fine. Okay. So let's rerun this. We still have to update our visualization, but we can run this with what we've got for now. Just look at what we print out to make sure that it worked. Maybe it'll be a bug. Okay, invalid syntax on line 58. Mistake here. Okay, missed an I. Okay, try again. Okay, so again, we have our tiny example with 2 facilities, 4 customers, and we see that we only open the second facility, which was located exit point 4. So we opened this one, which makes sense. It looks like it's closer on average. And every customer was served by the second facility. And okay, so that checks out. And you can see the skip logs here. So let's try and solve a harder problem now. Close this should actually terminate successfully. Okay. See if we can solve something a little bigger. So we'll say 20 facilities, 100 customers, and open 10. Let's get more output shown down here. Around this. Okay, and you can see again it solves it instantly. Going to skip logs, and a nice property of this problem. So the LP relaxation is here. It's not there. It's the second row, and it's short. This problem. I mean, it's not. We don't expect this generically, but it just so happens on these Euclidean instances that the LP relaxation is very good, and we solve it in one node. So it's a pretty easy problem. Okay, so we have an objective value of 14 here, and something that'd be nice to do is like to verify that this number is the correct order of magnitude, because it's kind of hard to verify the solution here. Although we did calculate this by hand, and that is coming from the solver, so that's a good sign. Let's see if we can come up with a good heuristic. So, okay, so how I like to think about this problem is, okay, I'll give a lower bound on the expected value of the objective for this random facility location problem, and then we'll see how it compares to the actual objective. For random instances. So will help us be sure that our code is actually right, because we never write any unit tests. It's also a good idea to write unit tests. So, okay, what I'd like to do here, I'm going to put my notes quickly. Okay, so, okay, here's the big idea. So let's say that we have m random points in the box, uniformly at random from 0, 0 to 1, 1. Okay, so here's a question. What is the expected value of the closest point to 0.5, 0.5. Okay, so you throw m points on the plane, and then you say, how close are they to the center of this box? And the answer, it is not completely trivial to do this, but you can Google it, so we don't need to think about it. And it is 1 divided by 2 square root m. Okay? We can just look this up. And so how do we relate this to the randomized facility location? I'll just provide a link if anyone is curious. When I Googled it, this is what I found. Okay, so for facility location, we have n customers, and for each one of them, we could kind of just, we have m facilities, and we say that the best we could do is that if we could pick the closest one of the m facilities. So we can't do this for all m customers because we have a limit, but we can only m facilities we can open, but we can get pretty close because we're going to pick facilities that are good on average for our customers. So this is going to be kind of in two ways an underestimate. In one way, it's an underestimate because we can't open all the facilities, and in the second way, these customers, they aren't in the center. They're at like a random point on the plane, so the closest facility to a random point is like a little bit further away. because it's not a torus. But this, this in these kinds of probabilistic arguments, these things don't really matter as n becomes large. So, so with n customers, we expect the cost expected, so a good lower bound on facility location solution there. So n divided by 2 times square root m. Let's print this out as well and see how close we get. This will kind of give us an idea on whether or not our code is correct. N divided by 2 times square root f. Okay. Add this to the output and rerun it. I didn't stop the last one. Okay, killed it. Okay, and we see our probabilistic lower bound was 11 and the objective value was 14. So order of magnitude, this is correct. So hopefully it's a good indicator that we did nothing too wrong. Okay, so it's a good sign. So what I want to do now is I want to fix our visualization so it actually shows the optimal solution instead of just showing the input data. And so how I'm going to do this is I'm going to color the facilities that we opened red, and I'll color the remaining facilities. So I'll color the ones we opened green and color the ones we did not open red. Then I'll draw a line from each customer to the facility that they were matched to. Okay, so this is a pretty easy change. Green if we opened, otherwise we're red. Okay. And here, I want to say, I'll look this one up again. Expert at matplotlib. Okay, found it in my notes. So, need to for our customer get their location, then we need to get the location of the facility, for customer of J, and then get the location. So this returns facility index and facilities. We'll unpack that, and now we draw the line from CXCY to FXFY. And so simple command add line to do this. Add in the X data and the Y data. So X goes CX, FX, Y goes CY, FY. Okay, now we should be able to see what our optimal solution looks like. So let's give it a run. Okay, and now you can see the green ones are the ones we opened, the red ones we did not open, and the customers only connect to the green ones, and they all connect to the closest green one we opened. So everything looks good here. So I mean, you could stop here, but I'm going to do one more advanced technique, and then we'll wrap things up. So what I want to do next is I want to add a callback to the MIP, so that way on every integer solution, we can update our plot. So we'll give it kind of an interactive animation. Okay, so to do this, we will need to, so I'll do this in kind of the most naive possible way. I'm just going to redraw the entire plot every time. I'm sure there's a better way to do it. I just don't want to spend more time with matplotlib to figure it out. And so I'll make a function to draw everything. Where are my functions? Okay, we got a call plot below. And we will need to parameterize this by the data we need. So we need to know which facilities are open. We need to know the facilities that are open, the customer locations, and the facility to customer mapping. And I think that's it. Okay. Facilities. Customers. I'll use a short name here because I don't want to end up with some kind of shadowing. So like you can see, everything is, all the variables are in the global scope here. This is a terrible way to program. It's fine for a script, but like it doesn't really scale to larger programs. So I just want to avoid a name collision with the outer scope. Facility is open and facility for customer. Okay, so we give them short names here. M is now length facility. S. Okay. Let's see if we can fix all these up quickly. It's open and facility for customer. Okay, I think that should hopefully still work. We can test it to make sure we didn't break anything. This after all of that. Run it, see if it still works. Looks good. Okay, so now we're going to call this function in the callback every time we find a new solution. Okay, so one other thing we have to do is we have to be able to extract this data every time we find a new solution. So facility and customers we have, but facility is open and facility for customers is what we need to extract. So we'll take this code. What needs to go into to have a new function that returns facility is open and facility for customer. Okay, so we'll have to pass in our facility variables, our customer variables, and the variable values. Okay, so we need to write this function now, and it's going to right here. Avoid any clashes. Okay. Tab, fix this a little faster. function that works super well. Okay. It's actually supposed to be. Okay, there we go. And X is not going to be defined in here. So we need the objective also, and the D's. Reorganize this quickly. Super careful with code like this, because if we have I equals 0, then this will throw an exception. I'm not going to have I equals 0 in this script, but better to do something a little bit safer. Okay. Wise. All right. I think I have. Successfully made a function out of this. Now, so it computes three things. Is the facility open? Which customer is served from which facility? This is too much, too short for a customer. Okay, let's try and invoke this function. See how we do. Nothing breaks. Delete this. And still work. Something here. Okay, still works. So now we are ready to write our callback. This is the exciting part. Okay, so where we call solve, we need to pass in a function that we're going to invoke on the solution to update our plot. So we need to do two things. We need to provide a callback registration object saying what events we want it to stop on, and then we provide the callback function itself. Okay, so registration. Say what events you want. This is a set. And we want to stop on solutions. It's easy. Now we need the callback itself. And so I'm going to define the function within, just right locally here, because we need to capture a bunch of variables. Okay. So this thing takes in a callback data. This is a MathOpt type. I'll add a type annotation here to make it a little bit easier to follow, because these types will be unfamiliar. And it returns callback result. Callback result will just be empty, because we don't need to do anything. So you can do things like interrupt or add constraints dynamically, but we don't need to do any of that. We're just going to update our plot. So, okay, so what do we want to do inside the callback? We want to make sure that we're on the correct event. We know it will be on MIP solution because this is the only event we're registered for. Can't hurt. Don't want any surprises. So secondly, we're just going to check that the solution is present. So this is allowed to be none. And MathOpt actually again guarantees that this won't be none when the event is MIP solution, but these asserts are pretty cheap. Okay, so now we need to extract our 3 pieces of data. Facility is open. So facility is open. I don't want actually I want to shadow the whole thing. Facility for customer and objective. And this is going to be the output of extract solution. Pass in X, Y, D, and our current solution. So callback get solution is a dictionary with variable values to floats. Okay, and now we update our plot. Where's that plot function? Just called plot, so we'll redraw everything from scratch. That's fine. Need the locations of all the facilities, locations of all the customers. And one change I'm going to make to the plot function, I'm going to pass the objective value in and set it to the title, because that will make it a little easier to follow. So okay, and pass this objective right here. We have one other call site for plot, and we'll have to pass the objective in. Okay, and I think our callback is good. So pass the callback into the solve function. This will be invoked at every solution. On callback data. I forgot one important thing. So this is just an oddity of matplotlib. Yeah, we're going to have to call plot.pause to give the renderer a chance to catch up after each of these invocations. So we'll slow our program down a tiny bit, but that's okay. So it's for 1/100th of a second. And anything else weird with plot? Okay, so we have to call plot.show. Okay, so we can call plot.show to start before we call solve. We'll have to call it the special argument block equals false because we don't want it to, we want the program to continue. Okay, so before we call solve, call plot.show. Let's try this. I think this will work. And we'll make this a little bigger as well so we can see our logs as we go. Happy about this. Keyword argument callback. So correct keyword argument is callback right out. Okay. Let's try again. Okay, So looks like we only ever got one solution here, unfortunately. Let me make the sleep a little bit longer so we can see better. So we'll sleep for 2 seconds for each solution. First solution was 13. First solution was best. Okay, let's make the problem a lot bigger and see if we can make our first solution not be best. I have another trick up my sleeve. We can just switch solvers if this doesn't work. Where's our problem size? Okay, so let's go with 50 facilities and 500 customers. This doesn't take too long. Okay, 53 is our first solution, 44. Okay, you can see it. Okay, so you saw the objective change, you saw the picture change, but we can do something a little bit more exciting. Since this is bit drive and animation, I will change to a solver which is going to struggle a bit more, and we can watch the animation improve since we worked so hard on that animation. So, as I mentioned before, CPSAT, it's very good on pure integer problems, but on this problem with all the applied integer stuff, it doesn't work. I think you probably just want to reformulate the problem a different way to give it the CPSAT. So there's a couple, we have to toggle the parameters here a bit because CPSAT is not, it's multi-threaded. We'll call the callback on multiple threads, and matplotlib does not like it when you call it for multiple threads. One other thing we want to do when you run CPSAT in a single threaded mode, you usually want to turn on interleaved equals true. Otherwise, so it's a portfolio solver and it does many different things, and you only give it one thread. The default behavior is that there's only one worker, so it doesn't exploit the LP and it can't get strong bounds. It's not even running the LP worker. If you run interleaved search equals true, then it will still run a full portfolio search, and it'll just have the different workers take turns cooperatively, and that way the LP solver will run so we can actually solve the problem to optimality. Okay, we don't need to solve this big instance anymore. We'll be able to see something interesting on a small instance we were looking at before. So 20, 100, and 10. All right, so hopefully no crashes. Let's see if we get a more interesting animation. Okay, so it starts out with not a great solution. Now we can see it slowly improving. And the bound is getting better as well. So 45, 12. And I think this in about 30 seconds or so it should solve the problem to optimality. Ways to go still, but this was slightly too big for CPSAT. Okay, I'm impatient. I will rerun this in a smaller instance. Oh, there we go, 26. Okay, maybe I'll just wait it out. We're getting pretty close now. Oh, something wrong with the animation. Animation looks like it's behind. Maybe I think I just didn't clear the plot from the, okay, that's gotta be it. Okay, So the animation is bad, as you can see. It's not what the solution actually looks like. I think I just forgot to call it bigger. Okay. So we need to get rid of the old lines. So plot.clear. Current axis.clear. Okay, I'll take current axis.clear. One more try and I'll make it a little bit smaller so it goes faster this time. Alright, this will be the last run hopefully. Okay, so we see we have a gap from 6 to 18, and you can see the solutions changing as you go. Got a lot of nodes connecting to things that are far away. So we get cleaned up pretty fast though. Okay, almost there. Gap of 1. Okay, there we go, solved with optimality. Okay, so I guess that's all I wanted to show today. So hopefully you enjoyed it and you're excited about using our tools. Thanks for watching.